Good evening everyone, I am Felix from 3rd BCSE section. I am excited to present our project on vehicle CO2 emission. In an era where climate changes is one of the most pressing global concerns, reducing carbon emission has become a priority. The transport sector, particularly vehicles, is a significant contributor to CO2 emissions. Accurate estimation of these emissions is crucial not only for assigning environmental impact but also for supporting the development of cleaner vehicle technologies and regulatory policies. Our approach to solve this problem leverages machine learning to create a productive model that estimates the vehicle CO2 emission based on various features. Instead of relying on traditional, often time consuming laboratory tests, we have used data derived methods to build a more scheduling and effective solutions. The dataset we used consists of several vehicle attributes like vehicle size, uh, engine size, fuel consumption, transmission type. By analyzing these features, we aim to develop a robust and reliable model that could provide accurate emission estimates. To achieve this, we have implemented multiple regression-based machine learning algorithms. We started with simple linear uh, regressions, which models that relationship between the single independent variables and carbon dioxide emission. While computationally effective, this approach was quite limited in capturing the complexity of emissions. As it only considered one factor at a time, the model's performance was measured using key evaluation metrics such as mean absolute error and mean squared error and R squared. Our findings showed that single linear regression had an R2 value of 0.75, meaning it could only explain 75% of the various emissions, which is insufficient for real world applications. To improve accuracy, we expanded our approaches using multilinear regression. This allowed us to incorporate multiple predictor variables, significantly enhancing the model's ability to capture emissions variability. With the approach, we achieved an R2 value of 0.87, improving production accuracy. However, we encountered issues with multicellularity, where some independent variables were highly corruptible with each other, causing estimated in the models of coefficients. To address this, we applied rate regression, a regularized form of linear regression that introduces. However, we encountered that issues with multi-collinearity, where some independent variables were highly corruptible with each other, causing instability in the model's coefficients. To address this, we applied ridge regressions, a regularity form where linear regression is introduced and 12 L2 penalty to reduce overfitting and stabilized with productions. Recognizing the non-linear nature of vehicle estimation, were also implemented k nearest neighbors and support vector regressions. KNN or non-parametric method provided better predictions by varying the emissions of similar vehicles. However, it required significant capacity power as the dataset size increased. Support vector regression, on the other hand, proved to be the most efficient model in our study. By utilizing kernel functions, SVR was able to capture complex on nonlinear relationship between input features and CO2 emissions, achieving the highest R2 score of 0.91 and the lowest prediction error. Our model evaluation showed that while similar regression models like linear regression provided a basic understanding, and advanced technologies like SVR and KNN often significantly improved accuracy. The ability to integrate machine learning into emission estimation opens new possibilities for the automobile industry and environmental public markets. Manufacturers can use these predictive models to design low emission vehicles, while government can leverage this data to formulate more efficient regulations for sustainable transportation. Despite our success, we faced several challenges throughout this project. One of the most key issues was handling missing and inconsistent data. Despite our success, we faced several challenges throughout the project. One of the key issues was handling missing and inconsistent data, which we addressed by applying importation technologies and further scaling. Additionally, the high dimensional nature of the dataset required us to carefully select and engineer features to avoid overfitting while maintaining model impersonability. Hyperparameter tuning played a crucial role in our project, optimizing SVR and KNN for better performance. Looking ahead, we used several opportunities for improvement. Integrated deep learning techniques, we could enhance productivity accuracy even further by capturing interactive patterns in the data. Additionally, expanding our dataset includes real-time emission for various during conditions could provide a more comprehensive and achievements in CO2 emission. Further works could also explore geopolitical analysis, incorporative traffic patterns, and environmental factors to refine out prediction further. In conclusion, this project highlights the potential of machine learning in addressing real world environmental challenges. By leveraging data deliver approaches, we can move toward more sustainable vehicle technologies and informed policy making. Our work demonstration that productive modeling is not just about the improving accuracy, it is about making meaningful contribution to the greener future. And now I will explain you about the coding. I am Felix and I am here to present our project on predicting vehicle CO2 emission using machine learning. This project is built on a data set containing vehicle specification including engine size, fuel type, transmission and fuel consumption, with the goal of accurately estimating CO2 emission. By leveraging machine learning, we aim to provide a scalable and data-derived achieve to analyze emission, replacing traditional time-consuming test methods. For the model section, we implemented multiple regression techniques. We began with simple linear regression, which gives us a basic understanding of a relationship between a single feature and a CO2 emission, but it had the complexity to capture real-world patterns. Moving the multi-linear regression, we incorporated multiple independent variables, improving accuracy but introducing multicellularity, which we are addressing using ridged regression. Since emissions are influenced by nonlinear relationship, we introduce k nearest neighbors KNN, which predicts based on similar data type points, and support vector regression SVR, which utilize kernel function. The map complex relationship for evaluating each these models using performance matrix like R squared, mean absolute error and mean squared error, and we found the SVR output outperformed all other models, achieving an R2 squared of over 0.91 and and the lowest prediction error. However, our work didn't come without challenges. High demonstrational data and correlated features required careful selection techniques. Computational efficiency was also a corner, particularly for models like KNN, which we optimized through dimensionality reduction. Hyperparameter tuning played a critical role, especially in optimizing the SVR models. Looking ahead, we see opportunities to integrate deep learning models for enhancing features extraction and incorporate real-time emission taking use of IoT based system. This advancement could further improve emission prediction accuracy and support the automotive industry in developing greener technologies. In conclusion, this project demonstrates the power of the machine learning in solving real world environmental challenges by providing accurate and scalable CO2 emission estimates or appropriate can contribute the sustainability, transportation and better policy making. Thank you and I welcome your questions. Thank you.